This lecture is going to be on natural frequency and resonance. A natural frequency is the frequency, or the period, at which a system naturally oscillates. We're going to be looking at the Tacoma Narrows Bridge and how and why it collapsed. We're going to be using natural frequency and resonance to help us make sense of it. But since objects can oscillate in various ways, many objects have several natural frequencies. For example, microwave ovens, musical instruments, cell phones. These are common devices that use the natural frequency of an oscillator. Another example, the strings of a guitar, right, like this one right here on fire, are tuned by adjusting the natural frequency of the vibrating strings to match musical notes. In other words, that little adjustment made to the string length changes the natural frequency so that we create these particular notes themselves. Here's a cool concept of using a magnetron, using a microwave. A magnetron is a device in a microwave oven that creates a wave driven by electricity. Some of the energy of this wave enters the inside of the microwave and cooks food. The shape of the magnetron forces the wave to vibrate at exactly 2.4 billion cycles per second, which is 2.4 gigahertz. This frequency is the precise natural frequency of water molecules. A microwave actually heats up food by transferring the wave energy to wave molecules. You heat up the water, you heat up the food. Resonance occurs when a periodic force has the same frequency as the natural frequency of the system. So we're going to watch the Tacoma Narrows Bridge collapse here in just a second. Essentially, it's saying that there's a periodic force that is increasing the amplitude over time. So if I were to create a push, I could graph this like so. Right? I push it at these timely intervals to either increase the amplitude or to keep the object oscillating at some distance. So if I'm swinging and I kick my legs at a certain timeline or a certain frequency, I can actually continue to increase my amplitude of my oscillation. But here we're going to look at the Tacoma Narrow Bridge and see why it collapsed. Here we have this older bridge. You'll see this in a second. This bridge and these winds picked up, and these particular, this is in Tacoma, Washington, and the waves began to oscillate the bridge. Essentially the winds, and it wasn't even an overly powerful set of winds, but they happened to resonate this. They were consistent with the natural frequency of this particular bridge. And what happens here was it began to oscillate because of a periodic force. These winds came. Notice you can see the trees here in the near ground. There was a car left on here. You're going to see this bridge oscillating, looking at it directly down the bridge itself. And that's simply, it begins to break apart. And the Tacoma Narrows Bridge itself is simply a result of the wind coming at it from the side. It began to amplify the oscillation, just like if you were to kick your legs on a swing, or if you were to push a pendulum as it's swinging, and it amplified it to a point where eventually it began to break itself and it began to destroy itself. There was a person that was stuck in it. He actually had a dog. He ran back to get the dog. The dog lived. This is what it would have looked like from looking directly on it. There's actually a person kind of walking in a crooked line here. That was the guy, the doctor. And if you want to watch the video, you can Google Tacoma Narrows Bridge collapse. And last but never least, we'll watch it fall apart. It's called a total collapse. And it begins to fall apart. And when it falls apart and breaks, it's simply the result of the oscillations would have had the bridge heat up, it would have broken the steel girders, and it would have compromised its structural integrity. Let's just see it one more time. Here's a picture of the car itself, and then here's the collapse. So resonance, back to the topic of resonance and natural frequency, resonance occurs when a periodic force, such as the wind, has the same frequency as the natural frequency of the system, and that's the reason why the physics behind the Tacoma Narrow Bridge collapse. Resonance occurs when there is a system in harmonic motion like a swing. when there's a periodic force, like a push, and the frequency of the periodic force matches the natural frequency of the system. Take a look here. A guitar string vibrates when plucked. When you apply a force, it'll oscillate that particular string to create a certain musical note. Here, if I'm swinging and I continue to get pushed by somebody, you can increase your amplitude, and that is the infrequent or frequent predictable push that's going to increase your amplitude. This would be resonance in this case. Here we can talk about the greater the amplitude, there's more energy, or the greater the frequency, there's more energy, and we'll be looking at that in a little bit. Buildings have natural frequencies as well. All buildings have natural frequencies. Several buildings have what's called a damper in here. So as the building begins to oscillate, particularly in areas that are earthquake prone, as the building sways this way, the damper actually stays here and it helps counterbalance the oscillation of the actual building itself. Here's a picture of the John Hancock building, or the John Hancock Tower in New England, in this case Boston, Massachusetts. It did not have a damper, and in 1972 or 73, I don't even know, not real sure about it, I just found this article, I thought it's kind of interesting. There were crazy windows just started flying out of this because it started swaying to the actual winds, and the winds just happened to come and start doing damage to it. And there you have it, natural frequency and resonance. And these are all just different pictures that you should be able to look at and help make sense of. There you go.